morning, dear colleagues, dear students. After the long pause, we will continue with our series in basics of nuclear chemistry, and today we will start the topic about the nuclear fuel cycle. And first topic will be the basics of nuclear fuel cycle, what it is, and where the radioactive waste are generated during the different activities within the nuclear fuel cycle. First of all, we will start with the question, what is the situation with the energy in the world? And from this data, you can see that there is quite a bad situation with energy in the world, because still there is around 1 billion of people without access to energy at all. So it's poor countries, and also as far as around 1/3 nowadays, or maybe 40% of all the people in the world rely on biomass. There are excess of deaths per year due to the exposure to the indoor air pollution or to the air pollution due to the use of coal or oil for production of energy, because all these materials, they produce quite a lot of different organic pollutants due to the combustion of the biomass, and thus these poisonous, hazardous materials that are released to the air and then inhaled to the human body. These compounds is increasing the death count rate in countries, and estimation that there is around 2 million excess of deaths per year due to this contamination of the airs. And what is the another question or the goal for the energy production in the future? That we have to decrease the fraction of the carbon-based fuel in production of electricity. So for example, today around 70% of all the electricity that is produced based on this carbon containing fuel. And as previous director of International Atomic Energy Agency was claimed that by 250, if we would like to meet the climate change goals, we have to produce around 80% of all electricity with low carbon fuel. That means it is the renewable energy, it's solar, wind power, hydroelectrostations, and also nuclear power plants. What are the safest and the cleanest sources of energy? This data, you can also see the detailed analysis of all the data by the link that is on the slide. And you can see so two parameters of energy production. The deaths per kilo or megawatt of the energy produced, and the emission of the CO2 in the atmosphere, also by the unit of energy produced. And you can see that these four energy sources, solar, wind, nuclear, and hydro power, are the most safest and cleanest. Even for nuclear energy, you can see that the death rates during production of the electricity by nuclear energy is very low. It can be surprising by population, but you can also remember that there are a lot of accidents in coal mines. There are a lot of accidents in oil productions. When these explosions they resulted in a lot of deaths and injuries of people, and of course during the application of nuclear energy there were also some accidents, but if we compare all the accidents, all the deaths and injuries that are caused by nuclear energy and by the coal produced energy, you can see that the nuclear energy is more safe. Also, if we compare the density of energy in nuclear fuel and in any other kind of chemical fuel, we can clearly see that as we know that the nuclear forces, the 5-6 orders of magnitude are stronger than any chemical forces, any chemical bonds, and we see that also the energy that is produced by the nuclear fuel is more or less 5 orders of magnitudes higher than the energy produced by the coal or gas. And this is a simple comparison that the 26 cubic meter of gas will produce more or less the same amount of energy as 26 milliliters of the nuclear fuel. So the nuclear fuel is much more dense in terms of energy, and it further means that for production of the same energy or the same power, we will need much less volume of our power plant when we use nuclear. It's just the comparison of the area that we need to build nuclear power plant or wind power plant or solar power plant, if we assuming the same production of energy around 1000 megawatt. So for nuclear power plant it will be around 1 square miles, and for wind turbines we will need let's say 400 times more area, and for solar panels we will need 75 times more area, more space to produce the same amount of electricity. Now there is a conception of so-called green square when we combine the nuclear energy, hydro power plants, solar and wind power. So for example, these types like nuclear energy and hydro power plants, they can serve as a sources of the constant energy, because neither hydropower or nuclear power depends on the daylight, on the climatic conditions, and thus these two types of energy they can provide a constant rate, constant power generation, and during the daylight, when we have a maximum of power consumption, we can include in the power net the solar power plants or wind turbines that can generate excess of the energy, and thus it is this combination can guarantee the safe production of energy during the whole day, in the night and during the daylight, and thus this combination is and all of these sources of energy they are carbon low in power production. So from these examples you can see that nuclear energy has a really great potential to play a role in secure electricity production first, and also nuclear energy can do it safely. Also, nuclear sources they can provide the long-term power production, and the lifetime of the nuclear power plants it is 30-50 years, and even in some cases even longer. Thus, for a pretty long time we can provide economically stable production of electricity. Also, if there is a nuclear power plant that is already operating, that means that the country or the region is more or less independent on the other sources of energy. But it is important for us as scientists, as future project managers, to build the trust in the public to nuclear energy. Because you know that nowadays there are quite a lot of radiophobic people who doesn't understand the nuclear, the radioactivity, and they afraid of all these technologies, and thus one of our aim is not only develop the new technologies, safe technologies, but also to try to explain all of these technologies to the public. And one of the important way to build this trust is to show how we can safely manage all the radioactive waste that are generated during the production of nuclear power and during the handling of any radioactive materials. But when we are talking about the nuclear energy, very often people thinking only about the nuclear power plant. But in reality, nuclear power plant is just only one part of the so-called nuclear fuel cycle. Nuclear fuel cycle, it is the whole operation that started from the uranium mining, then uranium extraction and refining, with further enrichment in uranium isotopic ratio, then production of fuel. Only after these quite complex steps, nuclear fuel can be put in the nuclear power plant when the electricity is produced, and after some time nuclear fuel can no longer produce the energy, and thus it's stored for some time, for a few years, in the special ponds, special pools in the nuclear power plant. And then there are two ways: either we directly dispose the spent nuclear fuel, and in this case we call this nuclear fuel cycle open nuclear fuel cycle, or we can reprocess the spent nuclear fuel for extraction of valuable components like plutonium and uranium. And thus we use the components of spent nuclear fuel to produce a fresh fuel that can be used again in a nuclear power plant. And in this case, it is called the closed nuclear fuel cycle. And what is the radioactive waste that can be generated during the production of nuclear power? So first of all, with the beginning of this term, radioactive means that material contains or contaminated with radionuclides. So radioactive waste certainly contains some radionuclides. As far as it is waste, that means that there is no use with current technology. So as for common waste, we call the waste that we can no longer use. But when we talk about the content of the radionuclides, not all the radioactive materials can be called radioactive waste, because if, for example, we also contain some radionuclides, natural radionuclides, and but it doesn't mean that our bodies are radioactive waste. To call waste radioactive, the content of radionuclide should be higher or greater than the levels, special levels that are established by the government. And if the content of radionuclides are above these levels, then we call the materials radioactive. If the radionuclides content is lower than these levels, then we can say that this material is non-radioactive from the point of the regulation. And also, we have to remember that as far as this radioactive waste contains radionuclides, all the radionuclides, they are decaying with the main law of radioactive decay, and thus the activity of all the radioactive waste is decreasing with time. That means that the hazard from the radioactive waste is finite. And it is not the case for common waste containing, for example, heavy metals like mercury. And this is a comparison of relative toxicity of different waste. And you can see that for many waste containing heavy metals like mercury or cobalt or cadmium, the relative radiotoxicity doesn't change with time, of course, because these elements are stable. And for radioactive waste, you can see clearly the decrease of this radiotoxicity with time due to the decay of radioactive radionuclides that are inside the radioactive waste. Depending on whether we reprocess spent nuclear fuel or not, this decay will take longer time or shorter time, but anyway, after some time, you can clearly see that relative toxicity of common waste or common heavy metals will be much higher than the toxicity of radioactive waste. Very often people don't think about it because, again, radioactive something radioactive is much more scaring people than the metals that they know from the school chemistry, let's say. But from the point of view of the safety, especially safety of future generations, it is clear that we have to think not only about the radioactive waste, but about this common household waste as well. Where the radioactive waste generated during nuclear fuel cycle? The answer is quite simple. At every step of the nuclear fuel cycle, we generate radioactive waste. In general, when we are working with radioactive materials, not only within the nuclear fuel cycle, but, for example, when we perform some research work in institute or in university or research center, or when we are doing some medical treatment, or we use radionuclide sources for industrial application such as tomography of some materials, or or like Röntgen used for X-rays are used for checking the even distribution of the material inside the detail, or some other application. So when we use radioactive material in any application, we will generate radioactive waste. So the simple answer again for the question where or when we generate radioactive waste is always and at every step of the use of radioactive material. So we will start with the again basics of nuclear fuel cycle since the very beginning. Mining of uranium ore. There are three general types of mining. It's open careers, it's mines, and it is underground leaching. Underground leaching is one of the most safest methods for uranium extraction from the ore, but the application of these methods really depends on the geological conditions where uranium ore is located. For example, so what is the underground leaching? We bury several wells that is called ingestion wells, and then we have wells where we pump out the solution containing uranium. So we pump in the solution, for example, of sulfuric acid that is going through the ore, and it dissolves uranium from the ore, and then this solution containing uranium is going out to the plant where the uranium extracted from the aqueous solution to organic solution, and then back extracted to produce pure uranium. So it is quite a simple scheme. Also, it looks like this in reality. So you have only wells in the field and nothing else. And when you extracted all the uranium from this ore, you simply remove all these wells, and then all this territory is reconstructed, is yeah, so going back to initial conditions very fast. Within 10-15 years, all these territories looks like in the very beginning. So again, it is ecologically friendly method for extraction of uranium. Of course, but again, we can use this method only in some specific conditions. For example, this ore itself should be permeable for the solution, for the leaching solution, and also there should be some hydro-isolated layers based on clays, for example. So these layers should not be permeable for leaching solution. So quite specific conditions, but there are few ores, few minings that used these methods in Russia, in Australia, in USA, and in some in Uzbekistan, as if I remember correctly. Yeah. Careers and mines, it's traditional ways to mine the ores. What is happening next? All these ores they are located like pyramids, and they are treated with the sulfuric acid, also from the head, from the top of this pyramid. So the solution is going through this mount of the uranium ore, dissolves uranium, and then this liquor is collected and then transported to the plant again to extract uranium and back extract as a pure uranium. During the mining of uranium, we produced, when we use these two types of minings, carrier or mines, we produce quite a lot of tailings from this uranium ore extraction. And these uranium tailings, they contains the natural radionuclides that were not extracted by sulfuric acid, and they are concentrated in these tailings. First of all, it's radium, for example, and all the decay products of radium, including radon. And during the exposure to the air due to the weathering effects or leaching effects, all these natural radionuclides, concentrated natural radionuclides, can go to the aquifer, to the natural groundwaters, and then goes to the housings, to the rivers, and to the plants, and etc. So these tailings in uranium minings are quite a big problem for the moment, because again, during the last 50 years, there were no such a lot of efforts given to prevent any radionuclide leaching. Of course, there was some lining, some dams, but still there are quite a high content of concentrated natural radionuclides, but these natural radionuclides, when they concentrated, they hazardous for people. And for example, average dose rate in this region dozens of times more than in the surrounding areas. So due to the content of radium, due to the release of radon gas, these tailings are dangerous for the neighborhoods. So next, the conversion of uranium. After uranium is extracted, it further purified by the different methods. One of them is the precipitation of ammonium diuranate. Then this compound is calcined and reduced to uranium dioxide, and then we need to enrich uranium in uranium-235 for certain reasons. So nuclear reactors, modern nuclear reactors requires from 2 to 5% of uranium-235, but natural uranium contains only 0.7% of uranium-235, so we have to enrich the uranium in this isotope. And to do this, we convert uranium to uranium hexafluoride. Why? Because it has quite a low sublimation temperature, so it goes directly from the solid state to the gaseous phase at temperature around 56 Celsius degrees. So it is very convenient to use gaseous phase to separate two isotopes. But during conversion, or so this step, the production of uranium hexafluoride from initial uranium-308 or uranium or ammonium diuranate or uranium dioxide. So this called conversion. So we produce uranium hexafluoride. During this conversion, again, at different steps, we have different waste during the during the purification of uranium. There is some tailings of uranium hexafluoride production that are stored in these barrels. Then the next step, so first was mining, then conversion, then enrichment of uranium. As I told you already that we made it in gaseous phase. For this, we can use different methodics. The first method was based on magnetic separation of different isotopes, but it consumes a lot of energy, and nowadays this method no longer in use. But two methods, the gas diffusion and gas centrifuges, they are still used and developed. So gas diffusion, the principle is that we have let's say barrel or tank with the porous membrane in the middle. We press the gas through this membrane, and the smaller molecules, of course, they penetrate easily. They penetrate easily through this membrane. Thus, the lighter the molecule, the faster the diffusion through the membrane, and thus the gas stream after this membrane is slightly enriched in a light isotope of uranium, uranium-235, And if we repeat this procedure several times, finally we can obtain the uranium, the gas stream with the sufficient enrichment of uranium. The gas centrifuge works different. There is no membrane, but there is a very big field that is produced by centrifugal forces. The rotating speed of this centrifuge is thousands per seconds, so it is very fast. So it's something like 100,000 per minute. And as far as the centrifuge is rotating very fast, there is a very big gravitational force that is formed inside the centrifuge, and again the lighter the element, the closer it to the center of the centrifuge, and the heavier the molecule it is located in another part of centrifuge, and thus we can separate two gas streams in this centrifuge, and one of the stream will contain the lighter element, and another the heavier element. And again, this centrifuge separation can be repeated many times. Actually, it is thousands of the centrifuges that are used for the enrichment of uranium. So they have different construction. In USA, for example, they use very tall centrifuges. In Russian Federation, we used small centrifuge like half a meter, and in USA they used 3 meters tall centrifuge. All of them have their own drawbacks and positive parameters, positive points, and it doesn't matter for the moment. And during all this procedure, what we produce? We produce the phase of enriched uranium. But that means that another stream will contain the depleted uranium. So the main waste that is produced during the enrichment, it is the depleted uranium hexafluoride that is stored in such barrels on the daylight surface. But from the radioactive point of view, it is more dangerous as a chemical waste, not as a radioactive waste, because uranium is a toxic metal, and this compound, uranium hexafluoride, can hydrolyze with production of hydrofluoric acid, and that is also poison for the human beings, and thus it is more chemically toxic than radioactive toxic. But is it really a waste? Because again, what is waste? Waste is that we can no longer use with the current technologies. But actually, nowadays, at least in Russia, there is a development of the fast nuclear reactors that can work with depleted uranium, with the pure uranium-238. That means that even at the current situation, this depleted uranium hexafluoride is no longer a waste. It is quite important source for future nuclear fuel. Then we have nuclear fuel fabrication. In general, nuclear fuel, for the moment, the main component of nuclear fuel in all the reactors, it is oxide fuel. Either it is pure uranium dioxide, or it is mixed uranium-plutonium dioxide, or simply called MOX fuel, so mixed oxide fuel. It looks like these tablets. They are very small. They are around 8 millimeters in diameter and around 2.5 centimeter in height. So these small cylinders, and they are placed in these claddings. It can be with different height, zirconium claddings with, for example, 3 to 6 meters, depending on the design on the reactor. It can be also then assembled in this square-shaped assemblies or hexagonal shaped assemblies, and these assemblies then goes to the reactor. There are different other kind of fuel that are used in, for example, in research reactors, in some transport reactors, but mainly in research reactors we can find this liquid fuel or some composite fuel. But nowadays the main fuel again it is the oxide fuel. During the production of fuel, how it looks like that the enriched uranium oxide or dioxide simply pressed in these tablets goes to the oven for calcination, then at temperatures around 1500 Celsius degrees in the atmosphere of the mixture of hydrogen and argon, they heated these tablets, so they are very compacted after this heat treatment and very mechanically stable, let's say. The compressive strength is very high, and after this heat treatment they are placed in these claddings. Not all the tablets are good in quality. After this heat treatment they are controlled either visually or nowadays special video cameras are used to control the quality of these tablets. But anyway, not all the tablets are perfect, and after this they are going, these bad tablets, they go back in the beginning of fuel production. They are dissolved, they are purified again, the uranium and plutonium, if there were plutonium, precipitated, and then after heat treatment of these precipitates, finally they come back again as a fuel tablet. But as far as there is steps for this purification, for the dissolution, filtration, etc., there are some liquid waste produced, and of course some solid waste. So as I already mentioned, these defected fuels are dissolved and refabricated, and we produce some radioactive waste. So finally, not finally, the next step that we place our nuclear fuel assemblies in nuclear reactors. Nuclear reactor in principle is very simple. Not if we just look on the scheme, it looks very simple, but actually all the systems they're quite complex, and there are a lot of different systems. But schematically, the principle of the work of nuclear power plant is following that. Inside the active core of the reactor, there is a nuclear fuel in assemblies. There are nuclear reactions are going. They produce a lot of energy, a lot of heat. Through these nuclear assemblies is water circulating, or yeah, so, water in modern nuclear reactors is not used not only as a heat carrier but also as a neutron moderator. So anyway, water is heated, and in reactors of like VVR types, this vessel, reactor vessel, it is a hermetic vessel, so water is heated to very high temperatures of 300 degrees under the pressure of 150 atmospheres, and this very hot water is going to this heat exchanger, where water in another contour is circulated, and in this heat exchanger, heat from this first contour is going to this second contour, the heat. This heat is heating the water in the second contour, and this water transforms to the steam, and this steam already then produced the electricity by rotating the turbine of electro generator. Then it is cooling down and goes back again to this heat exchanger. In heat exchanger, initially heated water in the first contour also cooled down and then go back to the reactor. So it looks like very simple, and this contour is closed, and where is the nuclear waste, but nuclear waste in nuclear power plants, they're mainly the resins that are used for purification of water that is circulating in different parts of the nuclear power plant, in the first contour, in the second contour, in the cooling ponds, etc. And these resins are used to sorb the radionuclides that can be released in these water solutions, and thus the water itself is very clean, but we produce the radioactive waste in the form of these resins that should be further be immobilized. And for example, in Russia there is no unified technique to immobilize these resins. Every nuclear power plants use their own technique to condition this radioactive waste. And what is happening with nuclear fuel inside the reactor? A lot of things is happening there. First of all, as far as the nuclear energy is produced due to the fission of uranium, that means that we produced a lot of new elements, new for the fuel. I mean, because initially in fuel there is only uranium and oxygen, or maybe uranium, plutonium, and oxygen, and no other elements. But due to the fission of uranium and plutonium, there are plenty new elements are produced. Half of the periodic table are produced inside the fuel. One of them are concentrated in separate phase, like for example noble metals. They form so-called epsilon phase. So it is a metallic particles or droplets that are formed of platinoids, also including some technetium inside. And they form the separated phases. So that means that fuel is no longer homogeneous material. Then, due to the heating of the material, there can be formed some cracks inside the fuel. Also, due to the formation of the gaseous products, this fuel tablets can crack. Also, you see on this example this bubbles on the surface of the uranium fuel. It is the channels through which gaseous products are released. Also, we form different fission products that can form complex compounds with uranium, with other elements. It is, for example, alkaline and alkaline earth metals that can form different salts inside the fuel. So all of these changes, all of these new elements, new compounds resulted in the changes of the fuel properties. So the changes in the thermal conductivity, in mechanical strengths. Also, there are some specific elements formed that are called neutron poisons, like xenon, iodine, samarium, and some others. That means that these nuclides, these elements, some of the isotopes can catch the neutrons and then doesn't give it back. So they steal neutrons from uranium, and that means that the efficiency of fuel is decreasing. So after a certain time of working in nuclear reactor, nuclear fuel is no longer efficient for the energy production. And when we replace this fuel, it's called the spent nuclear fuel. And then, there is a composition of this spent nuclear fuel. You can see that there are only a very small fraction of the fission products inside the spent nuclear fuel. Only around 3 to 5% of all the spent nuclear fuel, it is the fission products. Another 95, let's say, percent is a reusable material that can be used to produce a fresh nuclear fuel. And thus it is very important to reprocess this fuel. And again, if we reprocess the fuel, that means that we are closing nuclear fuel cycle. So we reprocess it again and again for separation of valuable components to produce fresh nuclear fuel. Or if it is not economically favorable for us, we can directly dispose spent nuclear fuel without any reprocessing, and then we talk about the open nuclear fuel cycle. If we so what are other benefits for reprocessing of spent nuclear fuel? This is again the dependence of the relative radiotoxicity of spent nuclear fuel. This line total radiotoxicity of this fresh nuclear fuel, if we don't reprocess it at all. And you can see this scale. It is time scale, but it is a logarithmic scale. So it is 10 to 1, 10 to 2, 10 to 3, 4, 5, 6, etc. So you can see that so this green line, it is the radiotoxicity of natural uranium ore. So that means that if our radiotoxicity will be the same as natural uranium ore, that means that that is called radioequivalency, that the amount of radioactivity that we took from the Earth and we put back is the same. And for the fresh nuclear fuel, spent nuclear fuel, you can see that without reprocessing, it will take more than 200,000 years to reach this radio equivalency. But if we take out all the long-lived radionuclides like actinides, like technetium and others, that means that in general, if we will have only fission products like cesium, strontium and some others, that means that already after 300 years we will reach radioequivalency. What does it mean? It means that if we would like to dispose this fresh spent nuclear fuel directly to the underground facilities, we have to ensure the safety of this facility for at least, let's say, 100,000 years. And it is extremely a difficult task because actually nobody knows what will be in 100,000 years. In this case, we have to ensure the safety only for 300 years. And actually, it is much more easier task because we can see a lot of different constructions that are much older than 300 years. So we can look at Egyptian pyramids that are more than 3,000 years old. Or so for 300 years we can guarantee the safety of the repository for high-level waste. But for 100,000 years, it is much more complex task. Nowadays, it is also possible to model all the processes, including seismic activity, including possible ice aging, and many others, other parameters to take into account with modern computers, etc. But still, for real safe operation, we can say that the reprocessing, that means extraction of all plutonium, americium, curium, and other long-lived radionuclides, with further transmutation of these long-lived radionuclides to the short-lived radionuclides, to the fission products, is much more safe than direct disposal of spent nuclear fuel. Yes, but even when we isolate all these long-lived radionuclides, what we will do with them further? And the answer is transmutation. Transmutation, that means that we induce fission of the of the nucleus, for example, americium or neptunium or curium, or we by neutron caption we can transform them to the shorter lived radionuclides, or for example for technetium-99 we can convert technetium-99 even to the stable element ruthenium, and thus we produce not even the shorter lived radionuclide but the stable material. So for transmutation, nowadays there is a special reactor called Brest, is under construction in Siberian region. All these transmutation reactions can be carried out in fast neutron reactors, and there are two of them in Ural region. They're called BN reactors that are under operation for already many years, and in this case the heat carrier is sodium. So for fast neutron reactors we cannot use water as a heat carrier, because water moderates neutrons and so decelerate neutrons. Thus we have to use other materials. In this case it's sodium, and for the Brest reactor the heat carrier will be lead. And as far as we transmute all these long-lived radionuclides, we not only reduce the long-term radiotoxicity, but we also decrease the volume of high-level radioactive waste. So in this photo, it's just a comparison of the radioactive waste that are formed by nuclear power plant, modern nuclear power plant, without reprocessing of spent nuclear fuel, and with the reprocessing of spent nuclear fuel. For separation, there are main methods that is called liquid-liquid extraction that is used nowadays, and the main method is a Purex process that was developed more than 50 years ago, and still it is the main method for separation of uranium and plutonium from all the other elements. And this method is based on the different redox chemistry of actinides, so uranium and plutonium, our main actinides in nuclear fuel, and all the other elements, including the rare earth elements. So Purex process also looks very simple. So first of all, we dissolve all the spent nuclear fuel in nitric acid. Then we extract uranium and plutonium by the organic solution of tributyl phosphate in kerosene. Uranium and plutonium goes to the organic phase. Then we wash this organic phase with aqueous phase containing some reducing agent. It can be iron 2 or it can be even uranium 4 because it reduces plutonium 4 to plutonium 3, and plutonium 3 is no longer located in organic phase but goes to the aqueous phase. And uranium 6 is still in in organic phase, and thus we separate these first two metals from all the other products, fission products, and then we can also separate them between each other. There are plenty of new systems that are developed for extraction of some certain elements, for example, cesium or strontium, because this cesium-137 or strontium-90 can be used in different radionuclide sources for different applications in technology. There are plenty of systems that are aimed to for selective extraction of different elements from this very complex mixture of different radionuclides, or for a separation of americium from curium, or from americium and curium from lanthanides, and etc. etc. But during the reprocessing of spent nuclear fuel, we generate quite a huge amount of liquid waste, because all these processes of dissolution, extraction, and then back extraction, they requires a lot of different solutions, and they resulted in the formation of the liquid radioactive waste, and this radioactive waste are stored quite differently in different countries, but both in Russia, in USA, in UK, in France, all these countries have nowadays problems with the liquid waste that were generated decades ago, and they are still stored in a daylight surface, either in these natural reservoirs or these cementitious tanks. But even these special tanks, they are leaking, and thus there are a problem of releasing of radionuclides from these reservoirs to the environment. And finally, one of the final step, no, not one of them, but the final step of the nuclear fuel cycle is the disposal of the either spent nuclear fuel in open nuclear fuel cycle, or disposal of high-level waste in the closed nuclear fuel cycle. In both of these approaches, in both of these nuclear fuel strategies, the main concept is the use of multi-barrier concept. What does it mean? That means that we put our radioactive material in many other shells. It's like a Russian doll called Matryoshka. So inside this main big doll, there is a small doll that represent our radioactive material, that is also radioactive material. It's not just a salt or solution. All the radioactive materials that are going to disposal, to repository, they are conditioned. That means that they are transformed to the form that are resistant to chemical action of water, resistant to thermal attacks due to the heat production, due to the radioactive decay. They're resistant to radiation effects. So we transform all these liquids or powders or whatever in a very compact strength form that calls matrix of for high-level waste. And this matrix containing all our radioactive materials then placed in special containers. These containers can be very complex. It can be a simple stainless container, or it can be a system of stainless container, buffer material, and another stainless container, for example. And then this container is placed in underground repository that is located at a depth of more than 300 meters, at around 450, 500 meters. And they are placed in special wells. And the space between the container wall and the wall of this well is filled with special buffer material. The main aim of this buffer material is predict or prevent the water contact of our container with water, and if the water one or another way is contacted with the container and it resulted in corrosion of the container and release of the radionuclides, then the aim of the buffer material is to sorb all the radionuclides that can be released from the container. And then, so it is 1, 2, 3 barriers. It's called engineered barriers. And then the natural barriers is the host rocks with the thickness of, let's say, 500 meters. And it's quite a lot of material for radionuclides to go through to reach the biosphere. So either it is open nuclear fuel or closed nuclear fuel cycle. In all of these nuclear fuel cycles, the main idea for the final disposal is the multi-barrier concept. Yeah, there are of course another sources of radioactive waste, as I mentioned in the beginning, that at every step when we use radioactive material, either for industrial application, research application, medical application, or whatever, we produce radioactive waste, and we have to know how to handle them safely. So as a brief conclusion, that the nuclear fuel cycle, or let's say nuclear energy production, it's not only in the nuclear power plant itself, at all the steps from uranium mining to the disposal of either spent nuclear fuel or high-level radioactive waste. Radioactive waste is the result of any activity using radioactive substances. Spent nuclear fuel not always radioactive waste. For closed nuclear fuel cycles, spent nuclear fuel is a very valuable source of uranium and plutonium. Fractionation of radioactive waste and reprocessing of spent nuclear fuel can significantly reduce the long-term radioactive toxicity of our waste. And currently, the main method for reprocessing is a Purex process. The main idea for storage and disposal of radioactive waste of any kind is a multi-barrier concept. And the last but not the least, that the hazard from radioactive waste is finite, and that is also one of the benefit of the nuclear energy, that the waste that arised from the nuclear power production, their toxicity is finite. So that is all from my side for today. See you next time. Thank you.